seen that free electrons in a solid, we derived the energy density. Allowed energy density. So I should write. Allowed energy density. Okay, and then now we derived Ne, number of electrons really occupy that energy states, and this is Ne times Fermi-Dirac statistics, right? And then each free electrons have 4 quantum numbers. Which should not be same to each other. 4 quantum numbers should be different, and that is the Pauli exclusion principle. Okay, and then this Pauli exclusion principle is related to the Fermi-Dirac statistics. Okay. Now we are going to talk about the band, energy band, and in energy band we have to focus ourselves in the fact that this free electron is not really free electrons in 2 senses. Number one, this electron cannot get out of that solid, get out of the system. Free electrons is confined in a system. If you want to take out that free electron out of the system, then you have to overcome the work function. We call that work function, right? And number 2, this free electron has to experience the periodic potential. It's just in a solid. We have to talk about the single crystal, right? The atoms has to be arranged in a regular pattern, so that the free electron has to, let's say, this is the atoms of the lattice. Then the free electron has to travel. When it travels along that this solid, then it has to experience the potential. If you draw the potential energy as something like this, then this free electron has to experience this periodic potential of the system. So in this 2 sense, this is not really free. even if we call that the free electrons, because it is not really belonging to any specific atom. We have to call that the free electron, but it is not really free in this two sense. Because of these two limitations imposed to the free electrons, now we have to think about the energy bands, okay? And in the book, we have three approaches to understand the energy bands of the free electrons. That is Kronig-Penney model and tight binding approximation and weak binding approximations. There are three ways to explain the energy bands which exist in a solid. Okay, so number one, Kronig and Penney model and tight binding approximation. And weak binding approximation. Well, briefly, we can see this Kronig-Penney model as a mathematical formulation of the potential that the free electron has to experience in a single crystal solid. So in this model, what we assume is that this is the position of the atoms in a single crystal, and then we call this is the V naught, the potential of the position at the atoms, located at atoms that the free electron has to experience, okay? And then we set at this point or Schrödinger equations inside this and outside this, okay? Here the potential is 0. Here the potential is 0. Here the potential is V naught. And then we have two Schrödinger equations, right? And then we have to think about what kind of energies allowed for the free electrons. Things like that. And amazingly, you can end up with some energy bands which should exist in a solid. Okay, tight binding approximation is kind of thing that the two atoms, and then you have electron energy states, and then when you get two atoms together, get close, then the outermost electron energy densities has to be overlapped, okay? And then it has to split. That is a tight binding approximation. And we want to see how, actually what we are going to plot is that the energy versus distance between the atoms x, okay? Then we see that the splitting of the energies in a very narrow energy gap so that it can be called a band, right? The weak binding approximation is that in a real free electron, energy is equal to h bar square k square over 2m. That is the kinetic energy of really free electrons, right? no potential energy for the free electrons. And then with this, if you plot that in E versus K diagram, E versus K, then you're going to have some kind of, this is the square energy is proportional to K square, so that you're going to have curve something like this. And then in this K, since it is, it should have a periodic potentials. We impose the periodic nature on this E versus K at these boundaries, so that we just modify at these ends, at these boundaries. All we have to do is just a modification at these boundaries. That's all we have to do for the free electrons moving in periodic potentials, okay? So that approach is going to be called weak binding approximations. And among these three, the Koenig-Penny model is good mathematical formulation to understand what's happening inside the solid, but really in practice, the number three is the most important thing, because we always working with the E versus K diagram of the solid, okay? So let's just briefly discuss about the 1, 2, 3 models to explain the energy bands and to understand why we really have to have a band. Now, before going into the details of this, what is a band anyway? Band. Band is kind of thing that the energy levels, allowed energy levels, forms a wide range of the allowed energies, and then the gap between these energies is 10 to the minus 12 electron volts or something. Very small. So that we may regard these energies as continuous inside this. And in reality, it is not continuous at all. Just the gap between the energies is just so small, so that it can be regarded as a band, okay? And the reason why we call this band is that this kind of band is separated to the next nearest band, something like this, okay? So that is a band 1, if you want to say, if you like. And this is the band 2, okay? And then in between these two, there's no energies allowed in the system, so that we call the band gap, energy band gap. So before I go into the details of this band, let me just give you an idea why we have to approach this band thing. Why do we have to understand this band thing, okay? Well, the conclusion of the discussion of this band is that the materials can be divided into 3. Number 1 is metal. That is a conductor. We call that this conductor, okay? And then number 2 is an insulator. That is just the insulator, right? And then number 3 is a semiconductor. If you distinguish the materials in terms of the conductivity, you can say there's 3 things. Now, what is the definition of the metal? The definition of metal is kind of materials where the electrons, free electrons, are sitting inside this band. Okay, that is the metal. And the insulator is kind of thing that the free electrons are sitting right on top of this, and this band is filled up. And the next available energy density state, energy band, is far apart by this energy gap. That is going to be called insulator. That's a little bit difficult. So let's see. The band gap in this insulator should be around 8 electron volts, typically. More than 8 electron volts or something like that. What is semiconductor? That the band gap is less than 2 electron volts. And that is going to be called semiconductor. In other words, this band gap is so small that by applying external energies like heat, light, whatever, even mechanical impact to this solid, then the outmost electrons sitting at this allowed band is going to be excited to the empty states, empty band, without any problem, easily. And that is going to be called semiconductors. So the reason why we have to understand the band formation in a solid is to understand the metal and insulator and semiconductor characteristics. Okay, so that is the main reason why we have to study on this band. Now, Koenig-Penny model, the first thing that we are going to do is on the text, just like this, okay, and then B and then 0. So you distinguish the region X is greater than 0 and A, and then X is greater than A, and then B minus A. Something like that, okay? In this region, the potential is V naught, the free electronegative experience, and in this region, the potential is 0. And then we are going to set the two Schrödinger equations, phi 1 and phi 2, okay? And then this Schrödinger equation has to have a continuity, mathematically well defined, which means at this edge, okay, at this edge and at this edge, it should mathematically well behave. The psi 1 and psi 2, psi 1 should be equal to psi 2, and then the derivative of psi 1 with respect to the x should be x equal to 0 and x equal to 0, right? That is the continuity characteristic. And the periodic potential says from this periodic potential we can create two continuity boundary conditions, like psi minus b is equal to e to the minus I k a psi a minus b. That is the periodic potential boundary conditions. And the x equal to minus b should be e to the minus I k a round psi over round x equal to a minus b, things like that. Okay, so we have four boundary conditions, four equations, and then we have four unknowns a, b, c, d, which is assigned to these two Schrödinger equations, a forward and b backward, and in this region psi 1 for psi 1, and then psi 2 we have a c for amplitude forward moving, and then backward reflection d. So we have a, b, c, d, four unknowns, and we have four equations, boundary conditions, so that we can basically solve the equation. And then the result is given in the text. And then the result is cosine Ka equal to alpha square minus beta square to alpha beta hyperbolic sine alpha b sine beta a minus b plus hyperbolic cosine alpha b cosine beta a minus b. It's rather complicated equations we end up with. And the beauty of this thing is that this cosine Ka should be greater than 1, minus 1, and less than plus 1 to make this thing mathematically well defined, right? And furthermore, these equations can be simplified if you can assume that the b is equal to 0 and v naught is as infinity, okay? The potential right at the atomic position should be very big so that v naught minus e is approaching v naught, okay? And hyperbolic sine alpha b is going to be can be approximated as alpha b, and the cosine hyperbolic can be approximated to 1 because of this, and the set P is equal to MA over H bar square B V naught. This is actually, we call this a delta function, right? This is a very, I think this is not A. This should be A, something like that, okay, according to this. This is very narrow and the potential is very high. We call that the delta function, right? So if you assume that the energy barrier is a delta function and set this P like this, then the cosine Ka can be simplified to P over beta alpha and sine beta A plus cosine beta A. Pretty much simple. This thing can be simplified to this. And then Now this should be greater than -1, should be less than +1 to make this the equation mathematically well behave. So as shown in the text, if you plot that equation in a axis like this, and then the y-axis is p sine beta naught and beta naught plus cosine beta a, and then x-axis is beta a, something like this. And then if you are going to draw that equation, and then that should be +1 and -1, something like this. And this equation is depending on the value of p here. And in the text, when p is equal to 6, that equation is going to oscillate something like this. Okay? And then if it is more than +1 and is less than -1, this is in between here and here. This is well defined. This is the allowed energy states, right? But it's beyond this +1 and then below this -1, like from here to here. Okay, this is not going to forbidden. Band in between this is less than -1. It's not going to be well defined. And then from here, +1, more than +1 range, from here to here, this is going to be a forbidden band 2. Forbidden band 2. And from here up to here, now this is going to be allowed energy bands. Something like that. And when you decrease the p values, then this forbidden band going to be narrowed, as you can see in the text, okay, from this mathematical formula. And if you increase the value of p, then this forbidden band is going to be increased. And the p, it has the b value here, and v naught value here. So if you increase the value of p, it means that the binding energy is very large between the atoms. So you can say this is the measure of binding energies of the atoms in a solid. So the band structure is pretty much related to the binding energies between the atoms, and the transition between the allowed energy band and the forbidden energy band, where here the transition here, things like that, that the transition happens at beta equal n pi. In other words, as you have seen that k equal to n pi over a. Every k corresponding to the m pi over a, we are going to have a transition between the forbidden and the allowed band, and then we call that Bragg reflections. This is the position where the Bragg reflection happens. Okay. And then the tight binding approximations. As given in the text, the figures, there's the illustration of the tight binding approximation in the case of sodium atoms, okay? And then when the R naught is equal to 3.67 angstrom, that is the equilibrium distance, lattice distance between the sodium atoms. And at that distance, already the outmost electrons have a overlapped band sitting in the energy band overlapped, so that sodium is a metal, is conducting materials. Now for weak binding approximation, which is the most important, in understanding the band, we know for free electrons, energy is equal to p squared over 2m, so that h bar square k squared over 2m. That is for the free electrons. So only kinetic energies, no potential energies. Equal to 0. That is the free electron, definition of the free electrons. And the important thing here is that every plus minus k equal to plumma m pi over a, then the standing wave happen because of the Bragg reflection, and then round E over round K should be 0. The standing wave means that in a one dimension, if you look into the one dimension picture, it means that the free electron moving to this directions, and if it is a boundary k equal to m pi over a, then it means that this electron is moving backwards. That is the Bragg reflections, right? So that it forms a standing wave, which means that at these boundaries, we are going to have the round E over round K should be 0. No more propagation. No more propagation as the first derivative of the vector should be 0. Okay? So what we are going to do is we first draw the E versus K diagram for the free electrons. And it should look somewhat like this. That is E versus K diagram for the case of free electrons. I never draw this beautifully. Okay. Okay, that is the E versus K. And then this curve is E is equal to h bar square over 2m k squared. Right? And then every plus minus m pi over a, the first, let's say pi over a, and then set 2 pi over a, he's going to be here, 3 pi over a going to be here. We're going to have vice versa. Okay, minus pi over a, minus 2 pi over a, minus 3 pi over a, something like this, right? And then this is a 0. So every of these boundaries, we are going to have a derivative value should be 0. Means if you look into this case in a magnified version, let's say here this is a pi over a, okay? And then if you want to make this thing derivative to be 0, it means that this thing has to be modified at this edge to, it should be flattened out like something like this in order to make the pi over a derivative should be 0. And then here at the same token, it should be flattened out. And then it follows like this. So that you can open up some of the energy gap here. Can you see this? Right? This is just to make round E versus round K should be 0. So what we are doing in this weak binding approximation is that we just superimpose a regular, periodic potentials on these free electrons at the boundaries, Bragg reflection boundaries. So you do this in every of this position, then you're going to see the flattening out here this much, and then the next is bigger than this, and then the next is going to be bigger than this, something like this. Okay? So if you draw that carefully, then what is going to happen is that you're going to see something like this. And then you're going to have a something like this on this next level, right? And then what you're going to do is you're going to move this thing to this side and move this thing to this side. then what's going to happen is that the first one is going to look like this, and second one is going to look like this. Right? And then the next one is going to it's going to show something like this. And here the next one is going to look like this. And then you're going to move this thing toward this. And then if you draw that on the top, I'm going to draw this thing like this. Okay? And then the next one is going to look like this. These are the bands that the free electron can have. These allowed energy densities, you should say. So from here to here, this is the allowed energies for the electrons to have. From here to here, this allowed the states the free electrons can have. And so this is the band. We can call that this is the band. Okay? From here to here, this is the band, energy band allowed. Energy band allowed for the electrons to have. And from here to here is going to be the band gap. The electrons cannot occupy the energy states because there is no energy state there. Simply. So it's amazing to see that the free electrons, if it is really free, then E versus K diagram should look something like this. But if you superimpose the periodic potentials, which the electron has to experience in a solid, in a single crystal solid, then suddenly we begin to see the band gap. The electrons cannot have energies somewhere in this energies, in between these energies. That is amazing things to see, right? So in a solid, if you draw the K and energies, and of course you can draw this Kx and Ky and Kz. Okay? We have three, in a Cartesian coordinate, we have three directions for this wave number. That is the vector, actually. Right? So if you draw E versus Kx, you can draw Kx, you can draw Ky, Kz in a solid, or you can draw Kx and Ky, Kx and Ky, and then you draw some energies on this, like something like this, right? That is a two-dimensional approach. Or you can draw the x and y and z, kx, ky, and kz, and then the three-dimensional way. You can draw the energy diagram in this three-dimensional way. Okay? And let's just see the E versus K diagram. And then in one solid, typically, it should show something like this. This is the typical drawing. What's going to happen? Let me exaggerate, something like this. So you can draw of infinity number of these bands in a solid, because this is not really the energy of electrons that existing in the solid. It just to show the allowed energy states. So just to allow the energy states, you can draw as many as you want. But from the Fermi-Dirac statistics, now you have to determine what energies really the electron can occupy, okay? And that is related to the temperature of the system. That is related to the external energies applied to the system, like electric field and the light and so forth, right? So let's suppose without any external energies and absolute zero temperature, for example, if the electrons occupy the outmost, the most energetic electrons, you can draw infinite number of available energy density states, but if you draw the energy bands really the electron can occupy, then at some specific temperature and the specific materials, you can draw the outmost bands the electrons can have, and then the next below the band, okay? And then the outermost energy band is going to be conduction band. And just next to, below to the conduction band, we call that the valence band. So in a normal situation, in the insulator, for example, we call this band gap. All right? Insulator case, this is more than 8 electron volts and so forth, so that the electrons are sitting in this valence band, and no electrons are going to be sit on the conduction band. We just call this available density state as a conduction band, not just the electrons really occupy this conduction band. And in the semiconductors, this band gap between the energy bands between conduction band and valence band is going to be less than 2 electron volts, right? Typically, if you say the typical semiconductor for the silicon, it is 1.12 electron volts, right? And gallium arsenide, indium phosphide, mercury telluride, all those have a different band gap energies. Gallium arsenide, germanium, that is the first semiconductor ever found. Germanium is, I remember it, that is 0.75. Gallium arsenide is bigger than this band gap is around 1.9 electron volts and so forth. Okay? So these are the semiconductors. What about the metals? Metals, some of the electrons are sitting in this conduction band. That is metal. Okay? So this band is not filled with the electrons, so that next available energy state is always there for the metals. So that this is the electrons in the metal is free to move. That's why it is going to show the conductions. Okay. Now, one thing I should we should notice in this E versus K diagram for the free electrons, in valence band, this is the E is equal to 0, and we call this the top of the valence band, right? And then the next higher band at here This is the bottom of the conduction band. The electron has been distorted because of the periodic potential right at here, right? And right at here. But when the energy, K, this is K is equal to 0. K approach to 0, we see at the top of the valence band and the bottom of the conduction band, it behaves like really free electrons. It is not distorted. It's away from the Bragg reflection conditions, right? So at this two region, we can say the energies of electrons sitting at the top of the valence band and bottom of the conduction band, we can say the energy is just h bar square k square over 2m, just like this. So we regard these electrons as a free electrons, no problem at all, okay? But the electrons at this position, at the Bragg reflection condition, we have a problem. We cannot equate the energy of free electrons at these edges according to this equations. But you should remember that electrons at these edges, we can say the energies of free electrons at these edges at this point is going to behave just like a free electrons. So you can apply that equation there. Okay, next lecture is going to continue on this discussion, weak binding approximation, and then we have we are going to discuss about the free carrier properties in a band, like a velocity, mobility, and mass of free electrons on Wednesday. All right.